Hi class, welcome back. Today we're gonna talk about limits at infinity. So this is gonna help us describe the behavior of a function as x goes to infinity. Now, when we are discussing this, it's important to discuss both directions. So as x goes to infinity, but also as x goes to negative infinity. So in this section, we'll determine the limit at infinity, which it could be different cases, right? If we have a finite limit, meaning that this is actually approaching to a specific number, a specific real number. So this will actually help us determine the horizontal asymptotes of a graph, and that's how we're going to be able to describe, this behavior as a horizontal asymptote. And we're going to be able to also determine infinite limits at infinity, meaning that when we're going to be able to determine whether this actually is approaching anything or is actually just going to there's no bound, that this is just increasing without bound. So here's an example real quick. If we notice this function, let me zoom into here. If we notice this function, this function, and a lot of things are happening in this region, right, between -4 and 4. But what we are also interested to see is what is going to happen in the future, like or as x goes to infinity. So as x goes to infinity, it seems like this is still increasing, and it seems like it's just going to be staying underneath this asymptote, right? This horizontal asymptote. So we want to be sure, right? We want to be sure. So we're going to have developed a tool to help us determine whether this is just going to stay underneath this x value, or is it just going to get closer to this value, right? Sometimes we only going to be able to determine whether it's approaching this value, right, and staying close to this value. Same thing on the other direction. Now, there's cases where it actually can approach to a different value, but a lot of times, like 95% of the time, the problems that we're going to be working in our class, they will be both approaching the same value. And so as x goes to negative infinity, the value of the function is increasing, but it's getting closer and closer to here, right? So our goal is to find this. Now, if you guys notice, it seems like it's creating this horizontal asymptote. Obviously, we can find this by using a table. All right, as x goes to negative infinity, we can see by plugging numbers on x that are getting closer to negative infinity, we see the number of the function is getting closer and closer to 3. As x goes to infinity, that means the values of x are getting bigger and bigger and bigger. The values of the function, right here, the values of the function are getting closer and closer to 3. So we can see here that that's what's gonna happen, right? So it's just gonna get closer to 3, right? It's gonna get close to 3. And now here's the formal definition, which I know it might be overstating or overwhelming, but this is very similar to what we have discussed before. Let L be a real number. The statement, the limit of f of x as x goes to infinity is equal to L. So the limit, that means the value of the function, is getting closer to L, means that for each epsilon greater than 0, there exists an m greater than 0 such that the difference between those two is less than epsilon whenever x gets really, really big, right? As x gets really, really big, these two are getting closer and closer to epsilon. The statement is similar to the negative infinity. The limit of f of x as x goes to negative infinity is equal to L, means that for each epsilon greater than 0, there exists an n, such that as these two numbers these numbers will get closer and closer whenever x becomes smaller and smaller and lower than n, right? So let's see this example here. As x, so what we're saying is that x becomes very, very big, greater than m. So we're saying that m is very big. So as x becomes very big, the values of the function, right, these are the values of functions, are just going to stay very close to L, right? The values of the function are going to go up and down, up and down, up and down, but they're going to stay within the difference of an epsilon, right? The difference between this point and that point, L and that point in the graph, will be very, very small, smaller than epsilon. Now notice that this means that it can go up and down this L value, right? So And that's sort of sometimes the misconception about horizontal asymptotes. We think that the function cannot cross this. And yes, it can cross it. Well, all we're saying is that the function is going to get closer and closer to this horizontal asymptote. All right, so that's how we're going to define horizontal asymptote. That will be is the line y equals L whenever the limit of fx equals L as x goes to negative infinity, or the limit of f of x equals L as x goes to positive infinity. Now, you could have you could have two horizontal asymptotes, right? This could give you one horizontal asymptote, and this could give you a different horizontal asymptote. But at most, you're gonna have two. So you could have no horizontal asymptote, you could have one horizontal asymptote, or you could have two horizontal asymptotes, and those are the only options. Let me say that again. You could have 0 horizontal asymptotes, you could have one horizontal asymptote, or you can have two horizontal asymptotes, right? All right. So before we jump into that, we're going to discuss a few sort of properties for the limits, and they sort of kind of follow from what we have discussed before. If the limit of the function as x goes to infinity and the limit of g of x as x goes to infinity both exist, then we can say that we can separate the two functions into their own independent limit. This also works for multiplication. Right, this also works for multiplication. As long as the limit for this exists and the limit for this one exists, both of them exist, then you can separate them. If one of them does not exist, right, let's say this is equal to 3 and this is equal to infinity, then we cannot sort of do this, right? And the same properties follow for negative infinity. Now here's another one that we want to discuss. This is a very interesting one, and we can think about why this is true. If I ask you, what is the limit of 2 over x as x goes to infinity? What is happening to x? What is happening to this value? This is becoming very, very big, right? It's like, and let's think about the biggest number you can think of, 1 trillion. So 2 over 1 trillion is going to actually get very, very small, right? So small that this is going to be 0.0000000000000000 whatever, right? So can you agree that this is going to get to 0, right? So the limit of this will be 0. In fact, this actually works if you have if r is any positive number. So if I have here a 2 or a 3 or a 7, right? So this will become will go to 0. And obviously c needs to be a real number. If we want to describe this in terms of as x goes to negative infinity, then this is still going to work out, right? If I put a negative in here, this is becoming a very, very negative number, right? Think about negative 10 trillion, right? So 2 over negative 10 trillion. What's going to happen with this number? It's going to get very, very small. It's going to be negative 0.000000000000000, right? To whatever, right? Whatever that number is. But it's still going to be a number very, very close to 0. So it's still going to go to 0. So in fact, anything that's in that form is going to approach 0. All right, so here's an example. So let's find the limit of it at infinity for this value. Well, we already know that the limit of 5 is 5. The limit of this is going to be 0, right? So we can separate them into two different limits. Apply the limit for this. The limit of a constant is always the same constant, right? There's no change because it's a constant. And the limit of 2 over x squared as x goes to infinity will be 0, right? Think about this number is getting huge. 2 over huge number is going to be 0. So 5 minus 0 is 0. So this gives you a horizontal line at y equals 5. Well, let's observe what happens if we try this with a negative. So if we apply this to the negative, then we're going to have the limit of 5 minus 2 over x squared as x goes to negative infinity. The limit of this exists because it's going to be 5. The limit of this is going to be 0, so we can separate them to each other. So that would be 5. Limit of 5 over as x goes to negative infinity minus the limit of 2 over x squared as x goes to negative infinity. The limit of 5 is 5, no matter what. The limit of this as x goes to negative infinity is going to be 0. So 5 minus 0 is 5. So it's also going to 5. So it shows that it also has a horizontal y equals 5. So what this is saying, if we think about this as a function, this is saying is that this function as x goes to negative infinity is getting closer and closer to the line y equals 5. And same thing in the other direction. So these two results allow us to describe the behavior of the function as x goes to infinity and negative infinity. So I want to point out here that what about, can we just jump in and just do this directly? Yeah, you can just say, well, you can guess that the derivative of this is going to be 5 and this is going to be 0, right? So you can just do it directly. You don't have to separate it to these two forms, right? This is the proper way to do it, but we already know that we can just jump into here and here, as long as this limit exists and that limit exists. All right, so this one is a little more interesting because we actually have to do some manipulation in order for us to be able to come up with the limit. So let's find the limit of this function. You have 2x minus 1 over x plus 1. Now, if you plug in infinity, right? If you plug in infinity, you're going to have 2 times infinity minus 1, which is infinity. Infinity plus 1 is infinity. So you have infinity over infinity, right? You get like this infinity over infinity, right? Well, this is inconclusive, right? Inconclusive. So we want to do better than this. So we actually can't, right? What we're going to do, whenever you have 0 over 0 or infinity over infinity, that means we can do some algebra and we can actually figure out whether this, what's the true limit. And the way we're going to do this is by manipulating the expression. So here's the original problem. What we're going to do is we're going to look at the denominator. Look at the denominator. What's the variable that you have there? X. What's the highest power of x? X to the power 1. So what you're going to do is, once you figure that out, you're going to use x to the power 1 and you're going to divide the entire denominator and the numerator by that. So it's technically doing this. 1 over x, 1 over x. So technically you're multiplying by 1 because you're dividing by the same thing. So you're going to have to distribute the 1 over x and the 1 over x. Why to both of them? Because this is a fraction bar and these are grouping together. These are grouping together. So this will be basically, this is going to happen. It's going to be this number over x, this number over x, this number over x, and this number over x. So that's pretty much the routine steps. So you can jump in from here to here if you recognize that x is going to be the number you're going to be doing, right? And so then you can simplify. And so you have 2 minus 1 over x, 1 plus 1 over x. Now you still have the limit and you must write the limit. Please continue writing the limit because we haven't applied the limit yet. Then once you have once you have this, then now you can apply the limit, right? The limit of 2 will be 2. The limit of 1 over x as x goes to infinity will be 0. The limit of 1 will be 1, and the limit of 1 over x as x goes to infinity will be 0. So you have 2 minus 0 over 1 plus 0 gives you 2 over 1, which is 2. And there you go. So in a similar argument, we can do that for the negative infinity, and it's very, very similar. So we'll do the same thing. We're going to jump these 2 steps, and I'm just going to jump over here because it's the same steps that we would have done over here. So they apply to negative infinity, right? This will be 2, this will be 0, this will be 1, this will be 0, right? And that's how we got the 2. And so we have, they're both going to the same limit. And there you go, right? I encourage you guys to try the next 3 examples here. And what we're going to notice here is when you apply those 3 examples here, and I want you guys to do that for these 2, right? The same steps that we did here. Do it for these 2. I want you to do those on your own. And what you guys will recognize is that in this case, there's some guidelines that we have discussed in college algebra, and there were that if you had the highest degree of the denominator is greater than the highest degree of the numerator, then in that case the limit of this or the horizontal asymptote happened to be 0, right? If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. So this gave us horizontal asymptote of 0. when they were the same, the highest degree of both numerator and denominator were the same, then we look at the ratio, right? 2 over 3. The degree of the numerator is equal to the degree of the denominator. Then the limit of the rational function is the ratio of the leading coefficient. And then whenever the degree of the numerator is greater than the degree of the denominator, then there was no horizontal asymptote. If the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. So you guys will see here that we get the same result if we apply the limit, right? So it's an interesting guidelines that we have used before, and now we justify it. So in this example, we can see that the highest degree of the top for the x will be x to the 0. So therefore, the degree of the denominator is greater than the degree of the denominator. So the degree of the denominator is greater than the degree of the numerator. So therefore, the horizontal asymptote is going to be 0. There you go. And the limit is 0 as well. So let's apply that concept on these two, right? So we're going to apply the limit, find each limit. Now this one is a little more tricky, right? It's going to be more tricky, so I'm going to show you guys how to find the limit of this. So this guidance are kind of nice whenever you're dealing with rational functions. But when you're not dealing with rational functions, then you cannot apply that guideline. And this is an example where you can't, because this is not a rational function because you have a square root as a denominator. So let's see what's going to happen. So if the limit of this, right, if the limit of this is what we're looking for, right, as x goes to infinity, then we know that if we plug in infinity here and plug in infinity there, we're going to get infinity over infinity. We're going to get infinity over infinity. This is not useful. Not useful, right? Not useful. Well, all we know is that that means we can do something about it. So what we're going to do is we're The goal is to put this inside this square root. But remember that when you're doing a square root, you must have a positive number, right? You can only take the square root of a positive number must stay positive. So this is the square root of a number, right? This is the square root of a number. That square root number needs to be positive. So this needs to be a positive number in order to be a square root of a number. So when you put this inside of this, well, then you're gonna have negative 1 over x all square, which now is just, it doesn't matter. It's just gonna be then you can just simplify it to be 1 over x squared, right? This is what I'm saying. Once you put it in there, this is gonna be 1 over negative x squared. But then you can logically simplify this to be 1 over x squared, or 1 over x squared, right? So, but nonetheless, we technically actually had a positive number. That's a positive number, and it needs to be positive when you go in there. So whatever you do in the bottom, do it to the top. So therefore, the bottom part is going to be the square root of 1x squared times the quantity 2x squared plus 1. And this is going to be under the expression of 3x over minus x minus 2 over negative x. What happens next is that these will simplify each other, right? They're going to simplify. The x's are going to simplify. And then that will give us negative 3 plus, and then negative becomes 2 over x. On the bottom part, we're going to cancel those two. That gives us 2 plus 1 over x squared. And then we can apply the limit, right? We can apply the limit. This is going to go to 0. This is going to go to 0. And then so we're left with negative 3 over the square root of 2. Well, that negative made a difference, right? Because now we can see that this is going to give us a different horizontal asymptote. And that's what happened, right? So key here is this. Look at that. And that's sort of important because that you guys will see that kind of pattern when you're dealing with the square roots. Now think about this. Just think about this. That if I'm writing a test, and these do not require for us to use the limit because we already have a guideline for this that we learn in algebra. Okay, that's cool. But are we using any calculus to this? Well, no. You could just technically use the guideline, right? You can just use the guideline for this. So wouldn't it be for me kind of nice if I want to test you finding this limit, that the only way that I can test you finding a limit will be something of this form, because it really challenges you that you can use the guideline, but instead you have to use the limit. So think about that, right? Maybe that would motivate you guys to try to think about this example. All right, so here are a few examples you guys can try. The limit for the first one will be does not exist, and the second, for the second one will be 0. Why? Well, this remember that this is a periodic function, and periodic functions work like this, right? This is a sine function. So as x goes to infinity, this is going up and down, right? It doesn't get smaller than that. It just stays within that amplitude. So there's no limit. There's nothing that is going to be approaching to. So the limit does not exist. What about part B? Well, this is getting very big, and this is staying within 1, right? The amplitude between 1. So what's going to happen is that you have a limit of 1 and negative 1, but this is becoming bigger and bigger, making this whole thing smaller and smaller and smaller. Even though it's going up and down, it's actually going to get very small, like this, as x goes to infinity. So that limit will be 0. All right. So we have a few definitions for infinite limits, right? There's times where the limit does not actually approach any real number, but instead it just goes to an actual infinity. So we'll have examples like that when they actually can't. It's just gonna go to some limit that is infinity. So for example here, if you're trying to find the limit of x cubed, then this is going to go to infinity, right? And this cube is just going to help it go more infinity. So there you go. So it's just going to be infinity. So it's almost like you're plugging in infinity. When you have a negative infinity, you're going to be multiplying negative infinity, so times negative infinity times negative infinity. well, it's going to be negative times negative times negative will be a negative, right? So you're going to go to negative infinity. So, and if you guys notice here, that's sort of what happens in the behavior of this function and the x cubed. It goes to positive infinity and negative infinity. Here are a few more examples for us to try. So here we're trying to simplify this. We know that there's the limit, this is not going to have a horizontal asymptote, and we can kind of verify that by, again, multiplying this by 1 over x, 1 over x. Where do we get the x there from? This x, we got it from here, right? If this would have been x squared, then that would have been x squared, x squared. If this would have been x cubed, then this would have been x cubed, x cubed. So it's always referring down to the denominator. So we're going to distribute, and we got 2x squared over x minus 4x over x, x over x plus 1 over x. This turns into 1, this turns into 1, and then now we have that 2x minus 4 over 1 minus 1 plus 1 over x. So as x goes to infinity, this is going to go to infinity, and this is going to go to 1. So you have infinity over 1, which is infinity. Similar argument for the negative one. So same steps, right? Same steps. And then but we end up getting here 2x minus 4, 1 plus 1 over x. In this case, this is going to negative infinity, right? Because x is going to negative infinity. 2 times negative infinity times 2 is negative infinity. Minus 4 is still going to go to negative infinity. This is going to go to a 1, right? Because this is becoming 0. So therefore, you have negative infinity over 1 equals negative infinity. So when you guys are thinking about this, when you guys trying to compute negative infinity, think about that you're sort of thinking a big number, right? So if you're thinking about like negative 1 trillion times 2, that's still going to be like negative 2 trillion. Negative 2 trillion minus 4, it's insignificant. It's still going to be like close to 2 trillion. So it's still going to be like negative 2 trillion, right? And over here, as you apply the negative infinity, this is going to become negative 0, like negative 0.0000. So it's going to go to 0. And so you're going to have 1 plus the 0. So you still sort of kind of like use the division. Like you're sort of using the infinity as a number, but it's not a real number, right? Now in these examples, because you didn't have infinity over infinity, then we are okay just computing this value over here as well, right? Infinity over 1, that was infinity. Infinity over 2, that's still going to be infinity. Infinity over 1/2 is still going to be infinity. The problem was when we started dealing with infinity over infinity, right? Infinity over infinity, infinity over infinity. That's when we decided, hey, let's do something about this. Let's figure out something that will help us be more precise. So if we have infinity over infinity or 0 over 0, we know that we can do some algebra manipulation to be able to actually find the true infinity, the true limit. Sorry. All right, so I hope you guys find this helpful. We're going to be using these concepts on 3.6 as well, as well as everything we learned in the previous sections. All right, if you have any questions, please let me know. Thank you.